Okay, guys, I think we're gonna get started. So, everyone, welcome to another Math Divulged class. Today, the topic of our class is how do you count? I'll be your teacher for today. We most likely will not have a TA, so bear with me if I'm unable to answer questions quickly or not. Okay, let's do this. Okay, I'll be using an iPad for this. Okay, so can you all see this? Just tell me in the chat. Okay, you guys can see this. Okay. Okay, so today we're going to be doing some basic number theory and counting. So I guess to start off the class, normally counting goes like 1, 2, 3, ... all the way until you get to like 9. And then once you get to 9, you move on to 10, and then you keep going. But what's special about 10 is that 10 is the first number that has 2 digits. And this begs the question, once we get to 9, why don't we just like create some new number? Like, I don't know, like a weird symbol for 10, maybe like a clover leaf or something. Why do we have to go with 10? I'm sure many of you know this, but the reason why we go to 10 at number 10 is that we have 10 fingers. And so when the humans are first counting, they would count to 10 on their hands, and then they would have to restart. So that's why 10 is like is an important number. So actually choosing which number to go to 2 digits is actually a very arbitrary decision. And it turns out we can actually count in different ways with a different number going to 10. So for example, maybe we can go like 1, 2, 3, sorry. We can go 1, 2, 3, 10, 11, 12, 13, 20, and on and on and on. And this would be base. And here, when I write 10, this is no longer the 10 that you're thinking about. This 10 is actually the same numerical value as the 4 that'll be up here, because it's the 4th number. So what we call this is what we call base 4. Because once you get to 4, you turn it into a 2-digit number, 10. So the way we denote this is if we have a number like 1, 2, 4, and we write a little small 4 over here, what this means is that this little 4 tells us we're in base 4. So it tells us we're in this sequence of numbers. So, oh yeah, it's not possible level 4. Oops, my bad. Let's do like 1, 2, 3. So if you want to convert this into base 10, or you want to get a feel for what this is, how would you do that? This is the question I'm going to answer. Let's clear everything. And let's leave this question at the top. You can think about it while I'm going through the rest of this. So an important hint is when you draw a number in like base 10, which is a normal number system, there are digit place marks, like place values. Each of these digits have a place. This over here, where the 5 is actually this is the ones place, or the ones digit. And this over here, the 6, is the tens digit. And over here, you get the hundreds digit. And here's the thousands digit, and on and on and on. So if you know what this means is that the ones digit has a value of 1 for every increment you do. If you change this 5 to a 6, you add 1 to the total number. And if you look at the tens digit, if you add 1 to the tens digit, you're increasing the total number by 10. If you add 1 to the hundreds digit, you're increasing the total number by 100. That's what these numbers mean. So we can actually write this out as 9 times 10,000 plus 8 times 1,000 plus 3 times 100 plus 6 times 10 plus 5 times 1. That's what this number is. Okay, so how do we do the same thing for base 4? Well, in base 4, things are pretty similar, except the digits are no longer 1, 10, and 100 digit. You instead get a ones digit, and then you get the fours digit, and then the 16th digit, or 16th place value. And the reason why I get 1, 4, and 16 is you have 1, then 4 to the 1, then 4 to the 2. So 1, 4, then 4 squared. Similar to how we had 1, 10, 10 squared, 10 cubed. So if we do the similar thing, we can get 1 times 16 plus 2 times 4 plus 3 times 1. And if we calculate this, what do you guys think this is? This is basic arithmetic. Okay, I see a lot of people with incorrect answers and some people with correct answers. So yeah, you're right, it's this. And this is in base 10 now. Okay, that's how bases work. So it's pretty easy to deal with bases less than 10 because we already have all the numbers for 0 to 9. So like we did with base 4 earlier, we already know the digits 0, 1, 2, 3, and that's enough for base 4. But what happens if we try and do bases that are greater than 10? For example, if we do something in base 20, well, the thing is 10 is no longer a 2-digit number. 10 is now a 1-digit number, but we don't actually have a symbol for 10. So what do we do? Like, what is 10 base 10? It turns out we can just use the letters. Like once we get to the end, once we get to 9, you just use A, B, C, D, on and on and on. This is just a standard notation. It doesn't matter too much. You're not going to use this too much. The most common situation in which you're going to see this, use these letters, is if you look at hexadecimal, which is base 16. For example, B base 16 would be 11 base 10. Yeah, if you notice something, the base value does not actually matter if you're just using the ones digit, because no matter what base you are, the ones digit still has value of a 1 per increment. So as a reminder, this is called hexadecimal. Referring to base 16. So base 16 is pretty useful in computer science, and also is useful in generating digits of pi. There's a theorem for digits of pi in hexadecimal. For computer science, I mean, okay, the most immediate thing you think of is using, what the computer actually uses is base 2, which is a string of digits, like zeros or ones in binary. And then this is equal to some number base 10. But that's oftentimes, it's hard for you it's hard for a human to understand what the strings of zeros and ones are. So sometimes when you use a computer, you would combine a number of these digits to form hexadecimal. And you get something base 16. And the way you do this is, if you look in base 2, this is the 1s digit, this is the 2s digit, this is the 4s digit, this is the 8th digit, and then we have a 16th digit here, the 16th place value here. So it turns out that these 4 numbers, before you get to the 16th place value, these 4 digits actually correspond to just 1 digit in base 16. And similarly, these next 4 numbers in binary correspond to the next digit in base 16. So when you have binary, every 4 digits can be condensed to just 1 digit in hexadecimal, which makes it easier to understand what's going on to a human being. So hexadecimal is pretty cool. Also, for digits of pi, it's 3.14 ... You can actually find what pi is in hexadecimal. And there's a theorem that will help you figure out what the decimals of pi are in hexadecimal. And this is because hexadecimal is a more intuitive and natural base than 10. Like 10, what's special about 10? There's not much special about it. But 16 is a power of 2. So there's some more flexibility with math there. And it helps you with computation of pi. I'm not going to go into that though. You should probably also go over decimal places in bases. So before, if I showed you like base b, like 12 base b, this would be like b plus 2 in base 10. But what happens if I give you like 12.3 in base b? What does 0.3 mean? Can you guys guess? Put your guesses in the chat. Okay, some of you are guessing correctly. So as we can use the same place value method I used before. If you look at 12.3 base b, this is the ones digit. This is the b's digit. It sounds kind of awkward to use, but that's kind of what it is. So what would this be? So the pattern is exponential. This is 1 is b to the 0, b is b to the 1. And as you go further to the left, you would increase the exponent that you raise b to. So as you go to the right, you decrease the exponent that b goes to. So this is b to the negative 1. So this is a 1 over b's place. So this is actually equal to 1 times b plus 3 times 1. Sorry. It's plus 2 times 1 plus 3 over b. And this makes sense in terms of normal digits. Like 12.3 in base 10 is just 1 times 10 plus 2 plus 3 over 10. And then the further you go to the right, you just divide by 100 or 1,000 instead. So this should be pretty intuitive. Okay. So that's base values. Now we're going to go into like a bit of a different direction. So it's pretty related, but I'm sure some of you or maybe you have heard of certain divisibility rules. For example, how do you tell if a number is divisible by 3? Like 1, 2, 3. 1, 2, 3 is a multiple of 3. Like 63 is a multiple of 3. 72 is a multiple of 3, etc. Yeah, a lot of you are getting already. The method to determine if a number is divisible by 3 is you add up each digit. So for 1, 2, and 3, 1 plus 2 plus 3 is 6. For 63, 6 plus 3 is 9, and 72, 7 plus 2 is 9 again. And the pattern is all these sums of digits are actually already multiples of 3. So since 6, 9, and 9 are multiples of 3, you get that all of these are multiples of 3. So that's the divisibility by 3 rule. Sum of digits is multiple of 3. Okay, so we can actually use what we learned before about bases to figure out why this is the case. If we have a number, I'm going to call it ABC, space 10. This line at the top tells you that A, B, and C are not being multiplied by each other, but they're just digits in like a string. I've told you before that this is A times 100 plus B times 10 plus C. So if you want this to be divisible by 3, what we can do is we can actually pull out 99 times A plus 9 times B plus, and then on this right hand side, we actually get A plus B plus C. So as you see, this number is clearly divisible by 3. So for the total thing to be divisible by 3, we also need this to be divisible by 3. And that's where we get the sum of the digits. A plus B plus C must be also a multiple of 3 for everything to be a multiple of 3. It turns out we can also do this for 9. As you can see here, all these 9, 9, and 9 terms are also divisible by 9. So we want A plus B plus C to be divisible by 9 for the divisibility by 9 rule. So the divisibility by 3 and by 9 rule are actually the same. Same as in like not exactly the same. I'm sure you know what I mean. So there are other divisibility rules. For example, there's a divisibility by 11 rule. I want you all to try and figure out yourself using the same place value method I showed earlier. So remember, try and figure out the divisibility by 11 rule. Okay, so the way you do this is if you have a number, I'm going to call its first digit A0, second digit A1, the third digit A2, and on until you get to AN. So what is this number when we expand it out? We have AN times 10 to the n, plus, if we can keep going all the way down to A3 times 10 cubed, plus dot dot dot, plus A0. So we can actually do a very similar thing before, where we pull out a gigantic multiple of 11, and then we have something remaining at the end that's something that's nicer to compute. So to do that, we would like to find multiples of 11 that are very close to these powers of 10. Before, we found multiples of 9 that were very close, like 9, 9, 9, 9, 9, 9, for example. Those are all just one less than the powers of 10, and they're all divisible by 3 and 9. So they're very nice. But we can't use all of these because, like, for example, this 9 and this 999 are not divisible by 11. But this 99 actually is. So we can use this 99. Well, we can't use a 9, we can actually use 11. Well, we can't use a 999, we can actually use 1001. So it turns out that if you keep going down the powers of 10, either the powers of 10 minus 1 is a multiple of 11, or the power of 10 plus 1 is a multiple of 11. So what we actually get is, if we factor out the 11s, we get a whole bunch of like 10 to the n, like minus 1 times an, and we get like 10 to the n minus 1 plus 1, the a sub n minus 1, dot dot dot. Okay, it'll be plus or minus 1 depending on how far n is. But at the very end, you'll be left with something like this: an minus 1 plus an minus 2, dot dot dot, minus a1 plus a0. And this term at the very end, it'll alternate between pluses and minuses because the multiples of 11 that are close to the powers of 10 alternate between being above and below the actual power of 10. So this greater thing over here, this thing is already divisible by 11. It's some multiple of 11 already. So to become another multiple of 11 by adding something, you have to add a multiple of 11. So the divisibility rule by 11 is actually you need the alternating sum of the digits to be divisible by 11. And the alternating sum just means you add one digit, then subtract the next digit, then add the next digit, then subtract the next digit, on and on. Another way of wording this is that the sum of all the odd position digits is equal to the sum of all the even position digits. Or like, okay, let's give an example for this. It might be hard to understand. If I have like 1, 2, 5, 7, 3, the sum of all the odd position digits is 1 plus 5 plus 3, which is equal to 9, while the sum of all the even position digits is 2 plus 7 equals 9. So therefore, the alternating sum would be 0, and this number is actually divisible by 11. So this method tells us how we can actually calculate divisibility rules in general. Past these couple, like there aren't, I mean, there's still like the obvious divisibility rules. For example, the divisibility rule by 2 That's simple. You just check the last digit, is it even or odd or not, etc. And that makes sense because when you expand the number, you get 10 times a bunch of stuff plus a last digit A0. So this is already divisible by 2, so we just need the last digit to be even. So that's simple. For divisibility rule by 5, it's the same thing. You have 10 times something plus A0. The 10 times something is already divisible by 5, so you just need A0 to be divisible by 5. So the 2-5 rule, or just like that. There are other rules, for example, the divisibility rule by 7, or etc. But those rules, those rules are not as useful. So I'm going to just you might as well just use long division for those rules. So the way to calculate those rules in general would be, if you look at 1, 10, 10 squared, 10 cubed, on and on, you would find the value, the multiple of your specific number that's closest to all of these. And again, you would just like, you would pull out as like close of a multiple of that number as you can, then you'd be left with like something at the end in terms of the digits. Then you can use that as your divisibility rule. So that's how you do in general, but it's not useful. So you guys probably don't need to use it. Okay, so those are divisibility rules. Now we're going to go into what's called modular arithmetic. I'm sure some of you have heard this before. Modular arithmetic. So I've already showed you how to count with different bases, but there's an even weirder way to count, which is you start from 0, you go to 1, you go to 2, you go to 3, and maybe you even get past 10, maybe you go to 12. But once you get to a certain number, you go back to 0, 0, 1, 2, 3, ... Then you go back to 0. And you repeat the cycle on and on and on. And this sequence is what you would call mod 13. Because at 13, you go back to 0. This is what modular arithmetic is. Every time, yeah, it's like a clock, actually. Well, a clock is actually like, a clock is a bit different. A clock is actually mod 12. You just shift by 1. A clock is very similar. So I've described it this way, but it's actually like a bit different than that. The more formal way of writing it is that every number like x you would write is equivalent to the remainder when dividing by n of x mod n. So this is like very scary, like math, like math jargon. I created this to be the remainder of x when divided by n. So what this 3-line equal sign means, this in modular arithmetic, when we write this, we say equivalent. So x is equivalent to what's on the right. Because in modular arithmetic, it's not that 13 and 14 and etc., the numbers above n, it's not that they don't exist. It's just that they're equal, or they're equivalent to a number that's smaller. So for convenience, we write the smaller numbers. So what this means is, if you look at like, let's look at an easier mod. Let's look at mod 5. So 2 is congruent to 7. Then why is 2 congruent to 7? Well, the remainder of 7 when divided by 5 is actually 2. like if you do this long division sign, you get 1 remainder 2. This 2 is special. So 2 is equivalent to 7. 2 is also equivalent to 12 because 12 also has the remainder of 2. 2 is also equivalent to 17. So it turns out that 2, 7, 12, 17, and on and on and on are all equivalent mod 5. So in mod 5, you really only have 5 different numbers. You have 0, 1, 2, 3, 4. These 5 numbers are all different from each other. But every single other integer is equivalent to one of these 5 numbers. So you essentially just take all the integers, you condense it down to 5. And some of you may be wondering, well, why is this useful? Why would we do this? There's actually there's a lot of very important reasons why we would like to look at this modular arithmetic. One, well, the reason why is there are many properties about modular arithmetic that make it useful when you want to do certain things. One of the properties that we okay, let's apply this to what we did before. When we wanted to find the divisibility by 9 rule. Okay, no, I think there's a better way to talk about this. Okay, the divisibility by 11 rule. I kind of told you that you alternate between having multiples of 11, 1 more than the power of 10 and 1 less than the power of 10. Like this. These are all multiples of 11, 1 more, 1 less. But I didn't really prove to you why that's the case. And we can actually prove that using mod 11. So we want to show that 10 to an exponent is equivalent to 1 or -1 mod 11. That's what I want to show. Just think about that for a second. Try and make sure you understand this. Okay. So what does -1 mean? Well, -1 is equivalent to 10. Just like before, where whenever you add 11, it doesn't actually change the fancy term equivalence class mod 11. When you add 11, it's still equivalent to itself. So how are we going to do this? Well, as you may notice, 10 is actually a very close number to 11 in itself. So 10 is actually 11 minus 1 to the nth power. And here is where here's where modular arithmetic is very, very powerful. We know 11 is equivalent to 0 mod 11. So we can actually call this 0 minus 1 to the n. I'm going to come back to why we can do this. So what this means is that we literally only have -1 to the n. And you have -1 raised to power. You just alternate -1, 1, -1, 1, -1, 1, etc. So clearly, we have the same alternating pattern we have at the top over here. So this is the power of modular arithmetic. When you have the mod appear inside certain things, you can turn it into 0 before doing other actions. This makes it very, very nice. Is this cool? I think this is very cool. So once again, 10 to the n is congruent to -1 to the n. Okay, let's prove how we can do this. So if we write 11 minus 1 to the n, there's this thing called the Binomial Theorem. If you If you don't know what it is, I'll just write it out for you. So this is actually equal to 11 to the n plus n times 11 to the n minus 1 times -1 plus n times n minus 1 over 2 times 11 to the n minus 2 times -1 squared, and on until you get down to n times 11 times -1 to the n minus 1 plus -1 to the n. So this looks very scary, very fancy, but all you need to know is that every time you go to another term, we have this like thing at the front, which is in terms of n, and then we have a power of 11 and then the power of -1. And the sums of the powers, the sums of these exponents is always n. For example, 11 to the n is just n. And here we have n minus 1 for 11 and 1 for -1. And those two combine to n. And like somewhere in the middle, you'd have like n over 2 and n over 2, or like 3 and n minus 3, for example. You would have like every like two exponents that sum to n. And the exact value for what these like starting terms are doesn't actually matter for our case. What matters is that when we go to mod 11, we can actually cancel out all these terms that are divisible by 11. This is 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 divisible by 11. It turns out every single one of these terms has an 11. So you would have a bunch of zeros. And the only term that doesn't have an 11 is this last term, -1 to the n. So it turns out we just get -1 to the n as before, as expected. I guess an important thing to know is that these beginning terms are always integers, which is why all these terms are divisible by 11. Okay, so that's the proof. So you can actually prove a lot of stuff with modular arithmetic, but what's important to know is that modular arithmetic is very intuitive. If you see a number that's 0, you can often just plug it in as 0 immediately. It won't always work, but a lot of times it will work. The times it doesn't work is when you have the number in the exponent. When you have like a to the 11 plus c, this is not congruent to a to the c mod 11. When you have stuff in the exponent, you have to be more careful. I don't think I'm going to go over exponents in this class. Maybe I will, probably later, but just keep in mind that you can't always do this. But everywhere else you can do it. If you have like 11 plus b times like a, this is congruent to b times a. Okay, what else to do? Okay, so we should talk about division in modular arithmetic? Are you guys ready for division? Okay, division is pretty complicated. Okay. So first, let's talk about mod a prime number. When you have mod a prime number p, things are actually much nicer. We can actually do division in this mod. If we have like a over b, what this actually means is you have a times 1 over b. And it'll turn out that 1 over b is actually equal to another integer. So this would be like A times C mod P. So when you have a division, you first need to find out is if like what the value of 1 over B is, what 1 over the base is. So how do you get what 1 over B is? So let's do something like this. 1 is congruent to C times B. So what is 1? 1 is congruent to any number times P plus 1. So normally 1 over B wouldn't make sense. You would have like a decimal. Like we can only have integers in modular arithmetic. So just having 1 over B wouldn't make sense. But perhaps when you add multiples of P, eventually you'll actually get to a multiple of B. So there'll be some value of K such that K times P plus 1 is actually a multiple of B. So choose K such that Kp plus 1 is congruent to 0 mod B. Remember, I wrote B here, not P, because we want Kp plus 1 to be a multiple of B, which means it's congruent to 0 mod B. Already, you should be seeing why mathematicians like to use modular arithmetic. It makes it so much easier to write like, this is a multiple of this is congruent to this, etc. So we choose that specific K value, and then 1 over B, or then we can clearly find what C is just by like dividing B over here. Okay, let's do some examples because this is very, very confusing. What is 1 over 2 in mod 5? You guys should try and find this on your own. But yes, 1/2 is equal to 1/2. I know that. What is the integer value of 1/2 in mod 5? I'm not seeing any correct answers. So people are giving me answers like negative 4.5 or other things. So in modular arithmetic, everything is actually an integer. So when you have 0.5 or 4.5, it doesn't really make sense until you turn it into an integer. Okay, so what we're going to do is 1 is congruent to 6 mod 5. So we're going to replace 1 with 6. Remember how I said earlier about we choose the value of K so that it's a multiple of the bottom number? That's what we're doing here. We're adding 5 until this top number is a multiple of the bottom number, and we get 6. And now we can clearly just divide out and we get 3. So 1/2 is congruent to 3. Similarly, 1/3 is congruent to 2. That's an easy one. Let's do a harder one. Let's do 1/3 mod 11. No, not mod 11, mod 13. Yeah, I'm getting some answers. Okay. Yeah, 1/3 mod 13. Okay, so this is congruent to 14 over 3, but 14 still isn't divisible by 3, so we don't like this. So we go another cycle. And if we add 13 again, we get 27 over 3, which is congruent to 9. So whenever you see 1/3, you can place it with 9. Okay, so you guys seem to have this down. And as a reminder, if you have something like 5/3, you can just split it as 5 times 1/3. And 5 times 9 is 45, and what is 45 congruent to? I think it's a 6. So you can do this as well. Just take out the 5, but you don't have to. You can do the same technique at the top. You can just add 13 to the top, and we get 6 as well. So this is these are two different paths that get you the same number. And this is another insight into why modular arithmetic is so powerful and nice. There are many, it's very intuitive. You can do anything that you think might work, and it actually works. And it gives you the same answer as other paths. So I don't know. Can you do it in decimal? So if you use decimals, you would end up getting the same answer, which is another hint as to why it's cool. I think it's best to stay in integers as much as you can, but you can do it. Oh, yeah, decimals everywhere would usually end up working out. Remember, this is for a prime, modulo prime. For other numbers that aren't prime, it's a bit weirder. But we can do stuff like, what is 1 over 4.5 mod 13? So the path I said before, where you find, where you just add 13 to the top until it's a multiple of 4.5, this will work, but I don't think it's not the method I would use. Instead, you do the intuitive thing of realizing that 4.5 is actually 9 over 2. So this is congruent to 2 over 9. And once you have 2 over 9, then you can start adding 13 to the top. You get 15 over 9, which is congruent to 28 over 9, which is congruent to 41 over 9. Which is 54 over 9, which is 6. I might have made a mistake there, but I think this is what you get. And you can even add 13 to the denominator. Yeah, yeah, I think you can. If you have like, okay, let me think of an example when you would do this. I guess if you want to calculate 34 over 4 mod 13, if you add 13 to the denominator, you get 17. And this will give you 2. If you went with other paths I've mentioned before, you could first reduce 34 mod 13, and then you get 8 over 4, because 34 is congruent to 8, and then you get 2 as well. So if you reduce in the numerator or denominator, you get the same thing. And once again, this is why modular arithmetic is powerful. No matter which direction you do, or like it's self-consistent. If you do steps that are allowed and you get to an answer, that answer will always be correct, and you can get 2 different answers. So it's powerful. If I had ended up getting 2 different answers here, then you wouldn't actually be able to use modular arithmetic for any proofs because there's no like answer. Okay. The only exception to dividing by things in mod prime is you can actually do 1/0, but this should be expected, right? 1/0 doesn't work in normal integers, so it shouldn't work here either. So what happens if we have division when we're looking at mod a number that's not prime? For example, what is 1/2 mod 6? Just think about this for a bit. What can you do with 1/2 mod 6? Okay, so at least one person has gotten it correct. Okay. So the thing with 1/2 mod 6 is if we try and do what we did before with adding 6 to the top, you'll find that we can never actually get something that's divisible by 2. And that's because we're adding something that's even to the top. So the top will always stay odd no matter what we do. So there's no way we can get it to be divisible by 2. And this is why we can't divide by 2 mod 6. It just doesn't work. You can never actually get an integer. So this is like big sad face. So it's really sad. So when can you divide? when can you divide by stuff? Well, it turns out that you can actually divide by numbers that are relatively prime to a bigger number. For example, you can have 1/5 mod 6. And this is because the GCD of 5 and 6 is equal to 1. This is what relatively prime means. What this means is that no matter what number we have on the top, by adding multiples of 6, we can eventually get a multiple of 5. So this tells us we won't ever get stuck in a loop. Because 2 and 6 had a common divisor of 2, whenever we added 6, like we're stuck in a loop of odd numbers. But with 5, we'll never be stuck in a loop of numbers like 1 mod 5 or something. So if you have complex numbers, try very hard to only divide by numbers that are relatively prime with that number. It turns out we can still do division with numbers that aren't relatively prime with our mod, but things get even more tricky. For example, what if we want to do 4/2 is congruent to x mod 6? Or sorry, that's not the best way of writing it. If I know that 4 is congruent to 2x mod 6, what does this tell us about x? So I said before that dividing is really weird when it shares a common divisor with 6, and 2 shares a common divisor with 6. So you can't just divide normally. You guys should take a while to think about what we can actually tell about x from this equation. Okay, we're running out of time with this class, so let me write this out. So what can x be? X could be congruent to 0, 1, 2, 3, 4, or 5 mod 6. And for each of these values, what is 2x? 0 goes to 0, 1 goes to 2, 2 goes to 4, 3 goes to 0, 4 goes to 2, and 5 goes to 4. So it turns out there are two possible values for x that have 2x is congruent to 4. So 4 congruent to 2x mod 6 tells us that x is either equal to 2 or 5 mod 6. That's kind of annoying for us to have, because you can't just divide by 2. Like, where does this 5 come from? Like, 4 over 2 makes sense, but 5, that's weird. So how you get 5 is, when you have 4 is congruent to 2x, what you should do is you should write 4 as 4 plus 6k is equal to 2x. If 4 is congruent to 2x, that means there's some value of k for which 4 plus 6 times k is exactly equal to 2x. Notice I'm using equal here, not congruent. This is not in mod. This is just normal numbers. What this tells us is that 2 plus 3k is equal to x. Equals, not equivalent. So 2 plus 3k equals x for some k tells us that x is congruent to 2 mod 3. If you remember earlier, we got that x is congruent to 2 or 5 mod 6. It turns out these two results are actually equivalent. Being 2 or 5 mod 6 is the same as being 2 mod 3. So the end result is that when you divide by a number that shares a common divisor with the mod, you also have to divide your mod by that common divisor. We divided by 2, and 2 is the common divisor with 6, so we had to divide 6 by 2. So if we have like 12 is congruent to 6x mod 9, we can get that 2 is congruent to x mod something else. Since we divided by 6, we have to find out what the new mod is. Can you guys think of what the new mod is? So some of you are saying mod 3 over 2. Do you guys know what mod 3 over 2 means? Mod 3 over 2 is not something you guys should concern yourself with for now. It's not that. Okay. So what this actually is we divide 9 by the GCD of 6 and 9. So 6 and 9 share a common factor of 3. So this would actually be 9 over 3, which is equal to 3. We can work this out with the second method as well. We have 12 plus 9 times k divided by 6 it must be equal to x, an integer. So 12 plus 9 times k is not always, 12 plus 9 times k is always divisible by 3. So what we can do is we can divide by 3, and we get 4 plus 3k over 2. Now the important part to remember here is that now we're dealing with mod 3 now, because we have 3k. And we know that that 1 over 2 actually has a value in mod 3. So this is like, so dividing by 2 in this situation does not actually change what mod we're dealing with. So this would actually end up being like 2 plus 3 times some other variable, which I'll denote as L here. So the mod stays as 3. Hopefully I explained this right. In the end, you most likely will not have to divide out by numbers in mod, but divide out by numbers that aren't relatively prime. But if you ever do, and you're ever getting confused, remember to always just expand out as like 12 plus 9 times k or something like this. It'll help you understand what's going on. So yeah, I guess it's kind of time for our class to end. As a closing remark, there's a lot more to modular arithmetic, a lot of theorems to use for when things divide other things. There's a lot of rules for exponents. Remember how I said that exponents don't act the same? There are lots of other theorems that are important to learn if you want to progress in math, in number theory, or in contest math. But so this is just an introduction for you all. And I've hoped I've managed to explain some of the importance and elegance of modular arithmetic, and hopefully you'll study it somewhere else in the future. So thank you all for coming to this Math Divulge class, and have a nice day. Thank you all.